Hello everybody, and welcome back to P2's homeroom. Today we are talking about simple machines split into a few different parts just to make sure we cover all of our bases. So when we are looking at simple machines, there are 6 different possible things that we can look at. We can look at levers, a wheel and axle, an inclined plane, a wedge, a screw, and a pulley. At the end of all of this, we'll also just briefly talk about what a compound machine is. So let's go ahead and jump right into everything. If I can find the mouse. Okay. So first up are levers. So levers are split into 3 different classes, but there are a couple of things that we just need to make sure that we identify first. So the first things first is when we're looking at a lever, there is a pivotal point right here called the fulcrum. Okay, and the fulcrum is a fixed point on the bar that the bar is going to rotate around. And with that, you also have the input and you have the output. Okay, so this right here, this arrow pointing down indicates that I would be pushing down. So this would be the input force. And then the other side, say I have a box right here and the box gets lifted in the air, indicated by the up arrow, that is the output force. So this is just kind of a generic example. And with all of this, something that we're going to be talking about is the ideal mechanical advantage. Or if we take all of these together, it equals the IMA. So whenever I refer back to the IMA, I'm looking at the ideal mechanical advantage. And so anytime I'm looking at a lever system, I am basically going to divide, that's not a divide symbol, I'm going to divide the input, actually I'm just going to make my life a little bit easier, we're going to abbreviate. I'm going to divide the input arm, which is how far my input is from the fulcrum. So I'm going to take the input arm and I'm going to divide that by the output arm, which is the distance between the output and the fulcrum. So say it's 1 meter each, I would have a 1-to-1 ratio. But if my input value is twice as long than the output value, then I would have 2 times the force being outputted, so on and so forth. Or if my output value was 2 meters away, then I would have to push down twice as hard, and so on. So this is just a generic example of what levers look like. So let's take a look at the first class. So the first class is pretty much the one that we were looking at, where we have our fulcrum, and I'm just going to abbreviate everything. So we have the fulcrum here in the middle, and then we have an input force and an output force. The key thing with this right here is that your fulcrum is in the middle of everything. So for a first class lever, the fulcrum is always between, I'm abbreviating BT, between the input and output forces. So some really classic examples of this are a seesaw. If you remember back to grade school, where you have one kid pushing up and then another pushing down. And of course, these can be flopped for your arrows. So this could easily be an input arrow going up and an output arrow going down. It just kind of depends. Scissors are another classic example of this. The way you take the scissors and push them together and pull them apart, it causes the ends to go in the opposite direction. Barbecue tongs are also another really good example of this. So the key thing with your first class lever is that the fulcrum is in the middle. This is the biggie right here. Moving on to second class layers. I'm trying to, come on. There we go. So second class layers, this time you can see that the fulcrum is on the edge, and for this one our output value is in the middle, but the input value is on the edge. So this time the output is located between the fulcrum and input values. Okay, a really good example of this is a wheelbarrow, where you have the wheel at the bottom that you can pivot around, and then you have the handles up at the front and or back, depending on how you look at it. And so you pick up the handlebars, but the borrow part of it, the bucket, the container, whatever you're trying to lift is stuck in the middle, and so you're not lifting the full weight. Generally speaking, you're only lifting about half the weight, just because it's half the distance, and so gravity is still holding a good brunt of it, so you're not having to lift as much. So again, key thing with this one is that the output force is in the middle. Okay, so pretty sure you could have guessed by now, but the third class of the lever, whoops, I'm gonna unhide the layer. My bad. Keep forgetting to actually select the correct layer. There we go. Alright, so again, we have our fulcrum on the edge, but this time you have the input value in the middle and you have the output value on the edge. So for a third class layer, the input force is located between, that is really close, between the fulcrum and output. So this right here. So basically the key thing for each type of layer is, or for each type of lever, is what is in the middle. If the fulcrum is in the middle, then it's the first class layer. If it's the output in the middle, then it's a second. Fulcrum is first, output is second, there we go, and input is third. So a good example of this is when you're sweeping with like a broom. So the pivot point is going to be up towards the top. Let's draw a broom out right here. So if you have your hand on it right here, this is going to be the fulcrum. Where your top hand is at is where you're holding it in place. The output value as you sweep it across the floor, and then typically you are going to take the middle of the broom, and that is what you are going to use to sweep it. That's one way. You could also use it as a first class lever, but traditionally this is what you're gonna see. And those are your three types of levers. So moving on to the wheel and the axle. So with the wheel and axle, this one's, well, all of these are pretty common, but for those of you that are looking into driving soon, this is a biggie. So with the wheel and axle, you have two discs or cylinders with two different radius. So of course the best way to take a look at this is the car, and so if you have the wheel of the car, you can rotate, whoops, bother. I have lost the mouse. There it is. My apologies, y'all. There we go. So when you are moving the wheel, like the steering wheel of the car, that is the input force, because that is what you are changing. So anytime we talk about the input force, that's what you are doing. The output force, there's a couple of different ones, but mainly is the axle that goes into the car that will eventually connect down to the tire wheels. Whatever you do to the input value, the exact same thing is going to happen to the output value. So generally speaking, the outer disc is your wheel, and your inner, I don't know why I have an extra I in there, your inner disc is your axle. Okay, but together these guys are going to rotate as a unit. Okay, and so when I am looking at the ideal mechanical advantage of a wheel and an axle, you're going to divide the radius of your input by the radius, it's an A, of the output. So I would take the radius of my steering wheel and then divide that by the radius of my axle. In this case, is going to have a really large to a really, really small ratio, but it could be vice versa. If you're looking at the actual wheels of the car, you would be moving the long cylindrical rod, and the wheel itself would be the axle, the output. And so yeah, so that is your wheel and axle. Okay. Alrighty, so up next we are looking at an inclined plane. So the inclined plane is a slanted surface along which a force moves an object to a different elevation. Basically, do you want to take the stairs or do you want to take the ramp up? My favorite example of this is if you ever go to UT, you have the hill, very famous, where you have like one of the halls up at the top. Well, the hill is ridiculously steep. I had to cross it many a time and it was very annoying. And so there were two different ways that I could do this. One is I could take the staircase going up the side, or if I had a little bit of extra time, I could take a sloped pathway around the side that would pull me up around the top. And so basically, whatever your horizontal to vertical ratio is. So for this, your ideal mechanical advantage is going to be when you divide the total distance, I'm going to abbreviate, the distance along a plane, so the horizontal surface, by the change in height. Okay, so basically, how tall are your steps? Are you going to take really, really small incremental steps, or are you going to take really, really large steps? And like I said, the hill over at UT is a perfect example of this, where you can literally take staircases going up the entire side of the hill. It's steep, and there's a lot of stairs. Or you can come around the bottom and you can nice and gently wind your way up around to the top. Either or. If you have a little bit of extra time, you can do this, or if you're usually in a rush, you're hauling yourself up the staircase. But I'm going to pause for this one, and we are going to continue the rest of this in another video, so I will see you all momentarily.